Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll explore how thread affinity can optimize OpenMP performance on the Fram Linux cluster. Thread affinity dictates how threads are assigned to hardware resources, such as CPU cores, maximizing performance by leveraging hardware architecture. By managing thread placement, we can enhance cache utilization and memory access, ultimately improving parallel program efficiency. Let's examine the hardware setup of the compute nodes on the Fram Linux cluster. Each node consists of two sockets, each containing 16 CPU cores, labeled from 0 to 15 in the diagram. Additionally, each socket includes a memory cache system. The memory cache system's role is crucial during parallel computing, facilitating data transfer between the main memory and the CPU cores. This system aims to alleviate the bottleneck caused by data transportation, ensuring efficient parallel computing. Note that there are two separate memory cache systems. Therefore, how threads are positioned will impact cache performance, consequently affecting the efficiency of parallel computing with OpenMP. In our previous video, when performing tests on Fram with 32 threads, the threads were randomly assigned to the CPU cores on the node. The diagram shows a possible random distribution of threads numbered from 0 to 31. It's clear that these threads are spread randomly across both sockets. This random distribution is suboptimal for cache performance, consequently impacting the parallel computing performance with OpenMP. Two crucial thread affinity variables are used to manage thread placement: OpenMP places and OpenMP processor binding. OpenMP places is an environment variable used to define the places where threads are allowed to execute. It allows you to specify the physical processing units, such as cores or sockets, where threads should be scheduled to execute. By setting this variable, you can control the mapping of threads to hardware resources, optimizing thread placement for improved performance. OpenMP processor binding is an environment variable used to control the binding of threads. This binding can enhance performance by ensuring that threads are assigned to specific processors, optimizing cache usage, and reducing memory access latency. In the illustration, when places are set to sockets and processor binding is set to close, the first threads, numbered from 0 to 15, are randomly assigned to socket 0. Subsequently, the remaining threads, from 16 to 31, are distributed randomly across socket 1. This arrangement means that the initial 16 threads share one cache system, while the subsequent 16 threads share the other cache system. In the next scenario, with places still set to sockets but processor binding set to spread, threads with even numbers from 0 to 30 are randomly spread across socket 0. Likewise, threads with odd numbers from 1 to 31 are randomly spread across socket 1. In our affinity testing, we'll bypass the socket setting and instead utilize the cores setting, as shown in the figure. In this configuration, with the cores and close settings, we observe that the initial 16 threads, numbered from 0 to 15, are sequentially placed on socket 0, while the subsequent threads, numbered from 16 to 31, are similarly allocated to socket 1 in a successive manner. Another option is to utilize the spread setting, where threads with even numbers from 0 to 30 are placed consecutively on socket 0, while threads with odd numbers from 1 to 31 are similarly distributed on socket 1 in a successive manner. We'll conduct affinity testing with matrix multiplication, maintaining the same matrix dimension of 16,384 as in our previous videos. Setting the value of n to 16,384 in our Python testing script is crucial for accurate performance calculations. I've modified the Python testing script to incorporate OpenMP affinity. We'll begin testing with OpenMP places set to cause and OpenMP processor binding set to spread. We need to include the OpenMP affinity setting in the execution command, along with specifying the number of threads to use. We streamline our workflow by employing the Intel alias to access the latest Intel Fortran compiler and matplot for the newest versions of matplotlib and NumPy modules. We transition to the standard compute nodes utilizing our setup Python script. Here, we'll request a single node with 32 cores to conduct our OpenMP affinity tests. Additionally, we'll specify our interactive job to wait in the development queue. After a brief pause, we are directed to the C8311 node to perform our multi-threading OpenMP affinity testing. We'll begin our testing phase by executing our Python script designed for testing purposes. Upon activation, this script will initiate our affinity testing procedures, providing us with valuable data and insights into the performance of OpenMP affinity. At the outset, the Python script shows the compilation command before proceeding with its execution. This deliberate step aims to maintain transparency in our workflow. Notably, we've integrated the IPO option into the compilation command. Executing both compilation and execution on the same compute nodes is vital to ensure consistency and avoid any potential discrepancies arising from differences in architecture between the login and compute nodes. We'll analyze the executable program's performance by varying the thread counts and using spread affinity binding. We'll compare the results of spread affinity binding, numbers highlighted in red, with those when no affinity is applied, numbers highlighted in blue. In this test, we see a speedup from 1 to 2 threads, achieving approximately 1.91 with OpenMP affinity. Without affinity, the speedup was about 1.99. When moving from 2 to 4 threads, we see a speedup of around 1.99 with OpenMP affinity. Comparatively, without affinity, the speedup was about 1.83. The results for the other thread numbers are omitted here, but they will be included in the figure produced with matplotlib. The testing Python script employ matplotlib to generate a plot depicting the relationship between wall time, CPU time, and thread count. Initially, we'll show the wall time values in the figure. Next, we'll display the CPU time values. To conclude, we'll include the speedup values alongside the wall time and CPU time data. It's apparent that multi-threading with affinity exhibits strong performance up to 32 threads. This underscores the importance of optimizing multi-threading with affinity for effective parallel execution. In our next affinity testing, we'll once more utilize the cause setting for the OpenMP places. but we'll modify the OpenMP processor binding setting to close. We transition to the standard compute nodes using our setup Python script, requesting one node with 32 cores for our OpenMP affinity tests. We instruct our interactive job to wait in the development queue. Shortly after, we are directed to the C8311 node, where we'll continue with our OpenMP affinity testing. We'll begin our testing phase with the Python testing script. The Python script initially displays the compilation command and then proceeds to execute it. We'll employ the executable program and test it with various thread counts and affinity setting using close binding. This enables us to evaluate the performance of OpenMP affinity. We'll compare the outcomes with close binding, shown in red, against spread binding, shown in blue. In this test, we notice a speedup when moving from 1 to 2 threads, achieving an approximate value of 1.87 with OpenMP affinity using close binding. The speedup with spread binding was about 1.91. Moving on to the transition from 2 to 4 threads, we witness a speedup of around 1.87 with close binding affinity. However, utilizing spread binding demonstrates better performance, achieving a speedup of approximately 1.99. The results for the other thread numbers are not displayed here, but they will be included in the figure generated using matplotlib. The testing script used matplotlib to create a plot illustrating how wall time and CPU time change with thread count. First, we'll display the wall time values in the figure. Next, we'll present the CPU time values. We'll finalize the figure by incorporating the speedup values alongside the wall time and CPU time data. We observed that using spread and close binding yielded similar performance on the Fram Linux cluster. In our upcoming video, we'll explore OpenMP affinity on the Betsy Linux cluster. Contrary to our findings on Fram, we'll demonstrate that spread and close binding exhibit different performance characteristics on Betsy. I am looking forward to the next video, wishing you all happy computing in the meantime.